we're moving on to the second part of our tutorial, which we agreed would be about graphs and transformation. As you saw in the previous part, we already spoke about the general graphs for exponential function. So we're going to just build on that. First of all, we agreed that we have the graph. We have two basic graphs, and these are a to the power x, where a is greater than 1, and a to the power x, where a is between 0 and 1, aka it's a fraction. So, this is just 1. And this is, those were the general graphs. Then we need to know that what if there were negatives? So, here, what if a itself was negative? So, if a was less than -1, then then we're going to be simply reflecting. Why? Because let's say we're doing -2 to the power x when it's 0 and when it's -1, when it's 0, and when it's 1. This will be simply negative half. This is going to be -1, and this is going to be -2. So as you see, it is increasing, it's getting lower and lower, but on the negative sense. In other words, it's going to be like this. So as you see, it's just simply the reflection in the x-axis from our first graph. And if we want to do instead here, if it's a fraction, so if we're talking about between -1 and 0, then we're talking about negative half to the power x, and if that's -1, 0, and 1, then this is going to be -2, this is going to be -1, and this is going to be negative half. And instead, it's going to look something like this. So again, it's just a reflection on the x-axis from the original one. And this is what happens when your a is negative. Now, normal transformations where you do shifts and stretches of x and y's are just, as I said, normal transformations. So just for the sake of an example, if we know that this is just a to the power x, what would we do if we have y equals to a to the power 2x instead? Then what simply happens is that if you have -1, 0, or 1, then you're going to be talking about -2, so 1 over a squared. And here you're going to be talking again about 1, and here you're going to be talking about a squared. So you're increasing, but if this is 2, then this is going to be 1 over 4, and this is 1, and this is going to be 4. So as you see, the change is quicker, it's steeper. Increasing the exponent by 1 makes it double. So in other words, if this is your normal graph, then you're just going to get here closer to the x, and here you're going to get faster up the y. And this is what makes it stretch on x. There it goes. And yes, so what you're doing is you're just doing here, putting x instead of this -1, so it's going to be a to the x exponent -2, and it's going to be 1 over 4, which is closer to the x. And on the other side, you're going to have a to the power 2, so if you have this as 2, it's going to be 2 to the power 4. Wait, to the power 2, so it's going to be 4, and that will give you a steeper curve. It is very simple and easy. Now, if we move on from this part, because it's very simple, as I said, we go back to the inverse functions. As you remember, when we wanted to find the inverse of 2x plus 3, we just switched the numbers, and we made y the subject of the formula, and that was it. It was very easy and simple. However, when you're dealing with functions like here, y to the power ax, this is very difficult. This is why we just have we have an actual function, new function for it, and this is our log function. So our log works like this. It has a base, and it has a number, and it's equal to the function. So this is our function. So first of all, you need to know that this is called the base, and this is going to be your actual number, and this is going to be the exponent. It's just the inverse. So if we have a number here that, as we said, y equals to ax, where 8 equals to 2 power 3, then when we're talking about the inverse of it, where y equals to log base a of x, we're talking about 3 equals to log base 2 of 8. So this is your base, this is the a, and you're raising it to the power 3 in order to get your 8. This is what's called the logarithmic function. And as we said, we have the natural exponential function e, because when you differentiate it, you get the same number. Now, this is where the natural logarithmic function will come. So as we said, where we're talking about log of base a of 8, and in order to get 3, then we're talking about a to the power 3 equals to 8, and then our a is just 2. Yes, this is how you solve it. Now, here's something. When we use L as a small letter, then we use a base. But if I just tell you you have a capital L log and we have 100, then your answer is going to be 2. Why? Because when we say log with a capital and we don't say the base, then we just simply mean log to the base 10. Now, let's go back to the e. If I told you we have log to the base e, uh, log to the base e of 1. No, let's say log to the base e of e, and this is going to be 1, because just e to the power 1 is going to give you e. It's simple. And log e to the power 1 is going to be 0. It's simple like that. But we don't have to write log e, because we created a function which is called the natural function in order to express this. We use what we say ln. It's ln. When we say ln, we just simply mean log to the base e. So here when we say ln e, the answer is going to simply be 1, because these are the exact same. And that would be the natural logarithm and the natural number could use. I know the inverse functions were supposed to come last, but it was very befitting here to understand it. Now we're going to move on to the applications.